Hi, my name is Matt Ozales, and I'm an RF engineer at Keysight. In today's video, I'll go over how to design a Class E power amplifier. This topology is popular because it offers very high efficiency, but there are some trade-offs and design challenges that you'll have to understand in order to be successful. The objectives of my presentation are first to cover the basic theory behind this circuit. I'll go over how it works and show you some basic design equations, and from there I'll synthesize an almost perfect Class E circuit and simulate it using a basic test bench. Then I'll demonstrate an approach to convert this ideal circuit topology into something that's more realizable. And this analysis is built on concepts and techniques discussed in a few of my previous videos, and you can find them at the link below. So what I'm going to show today is a superior approach to starting a Class E power amplifier design. And to validate this, I'll provide simulation results for both an internally developed GaN model and also a commercially available GaN mimic from Cree. And at the end of this video, you can download the workspace I use, which contains all of the design templates and synthesis tools that I'm using here, as well as the internally developed gallium nitride model. These utilities are going to save you a lot of time in your design work. First, I think it's important to understand the concept of a switching mode power amplifier. As opposed to the conventional classes of operations, switching mode amplifiers use a transistor like an on-off switch. So when the switch is closed, AC current flows into the switch, and when the switch is open, current flows into the load, which causes a voltage. Now ideally this results in extremely square voltage and current waveforms with almost no overlap, so very little power is dissipated in the switch's heat. Now at first glance it might seem like this amplifier should be extremely efficient, but it turns out that about the best you can do here is around 81% efficiency with this topology, because a lot of the power ends up getting lost at the harmonic frequencies, not being transmitted through the fundamental. Okay, so how can we improve this? To control the harmonics, we could put a resonator at the output. This circuit is a short at the fundamental and an open at all the harmonics. And so the action of opening and closing the switch will force a sinusoidal current to flow through the circuit. But if you think about it a little more, there's a problem here. When the switch is closed, AC current will flow out of the resonator into the switch, which is fine. But when the switch is open, the resonator will try to pull back current from the switch to make a sine wave. And there's no path for this current to return because the switch is open. We can address this by putting a capacitor in parallel with the switch so that when the switch is open, current can return back to the resonator through the capacitor. So the sinusoidal current waveform will alternate flowing between the switch and the capacitor. Let me explain intuitively how this circuit works. The key is to minimize the dissipated power in the switch, which occurs whenever voltage and current exist at the same point in time, and this is especially important at the opening and closing points of the switch. Since the point where the switch closes has the biggest potential for high current draw, it's good to have both voltage and current equal to zero at that point. When the switch opens, it's acceptable to just have the voltage be zero, since current won't get pulled into the switch. These are of course boundary conditions for time domain circuit analysis. Here I'll assume the switch will close at 0 degrees and open at 180 degrees. So the current through the switch is really just a DC offset sinusoid, and we'll need to do some phase shifting in order to ensure that the power dissipation requirements are met at the closing point, and this is done partially by adding a series inductor to the circuit. As for the voltage across the switch, this is really just the voltage across the capacitor, which is the integral of the current over the period when the switch is open. The switch forces steady-state voltage to 0 when it's open and current to 0 when it's closed, and if things are designed correctly, this set of waveforms has the potential to be 100% efficient. Something that I think designers realize pretty quickly when they start working on a Class E circuit is that the equations are not all that easy to find. The original work assumed a 50% duty cycle and used that simplification to derive equations with some seemingly random factors in them. And even this simplified analysis showed that the voltage and current swings tend to be very high multiples of the bias, and that really leads us to the big issue with Class E power amplifiers. They really push reliability because the signals start to exceed the safe operating limits of the device. And since the magnitude of these swings is highly dependent on duty cycle, always using a 50% duty cycle is not a good idea. So what about equations that include duty cycle? Well, they've been around for a long time. They were originally derived by Dr. Robb, but they just aren't compact, so the resulting values are usually expressed in graphical format. And that's why you might see PA designers sitting at their desk with the magnifying glass trying to interpolate values off a graph, which I've done myself many times. As a designer, this is where I find some of the unique capabilities of the ADS data display to be very useful. I've been able to put these general design equations directly into my data display, and this allows me to set up a Class C circuit synthesis in a way which is interactive makes the design process very straightforward and saves a lot of time. And you can download this Class C power amplifier synthesis utility with the workspace that I'll provide at the end of today's video. Okay, so let me demonstrate. On the left-hand side, I enter the device parameters, so maximum voltage and current, knee voltage, and internal parasitic capacitance of the device. And then I use these sliders to set my performance specifications, so frequency, DC supply voltage, output power, and conduction angle. And based on this, the tool synthesizes a Class E circuit for me. On the right-hand side, it generates the Class E voltage and current waveforms across the switch and analyzes these against reliability constraints. The tool essentially looks at all possible conduction angles and returns only waveforms that meet these requirements, and then notes where these conduction angles occur. And on the bottom, the circuit values are plotted entirely versus conduction angle. The valid range for reliable operation occurs for conduction angles between the markers, and there's also a marker that shows the particular conduction angle that I've selected. If the angle is outside of the markers, the device limitations are being exceeded. So I want the conduction angle to be between these vertical reliability markers. And sometimes it's not even possible to realize Class E operation with any conduction angle, and if that happens, the markers collapse and a warning message pops up. Now I'll show you how to use this. So here I have an internally developed gallium nitride model that I can share with you as part of my workspace, and I'm going to design a power amplifier with it. My device's absolute maximum ratings are shown here that drain to source voltage is 100 volts, max AC current is 12.5 amps, and DC current is 6 amps. Okay, so I'm going to start out by generating DC IV curves for my device. I've got a utility which interactively draws a load line. I'll make that downloadable for you as well. And based on this, I can easily design a Class B power amplifier at 40 volt supply to get about 96 watts of output power and still meet my device's maximum ratings. What about Class E? Well, I'll generate this design using the synthesis tool. I've already entered my device's reliability limits and intrinsic capacitor value, and I'll use the sliders to set the frequency to 1 GHz, the supply voltage to 40 volts, and the output power to 96 watts. Now the synthesis tool finds the range of conduction angles that I can use. These are conduction angles between the black vertical markers, and in this case it's an extremely narrow range to operate in. I have from about 110 to 120 degrees. Now hopefully you can see why it's so critical to have design flexibility as far as conduction angle. You need this degree of freedom to operate reliably. At 180 degree conduction, the device would fail. It's not always realistic to achieve Class B type output power for Class E with the same condition. This is the price you often pay for high efficiency. So if I lower the supply voltage and the output power requirement, then the design window opens up enough to do a reasonable cut at a PA. Now I have a wider area to work with as far as conduction angle, but still the absolute upper boundary is 180 degrees. So I'd better pick my conduction angle lower than that. Here I'll go with 160 degrees. Now I have the ideal Class E circuit, the values are shown here, and all I need to do is validate it. I built a simulation bench to do that. It's actually very simple. Basically I just modeled the transistor using a switch component and brought in the circuit values from the synthesis tool, and I will run a harmonic balance simulation on this to see how well the results agree. Well, as you can see, the simulation results actually agree very well with the predicted waveforms. The solid lines are the simulation, and the dotted lines are predicted from the synthesis equations. And I've looked at this over a wide range of circuit conditions, and I think the design equations that I've got here are generally very good at predicting the large signal result. And also, for every case I've tested, this idealized large signal simulation gives me about 99.9% efficiency, and that's as good as a starting point as you can possibly get. So now let's design a real circuit using this as a foundation. To make a realistic amplifier, what we really need is a way to translate this ideal circuit to a more physical configuration. After all, things like perfect DC feeds don't exist. So first let's look a little closer at what this switching topology really does, and I think trigonometric Fourier analysis is very useful here. So let's take the simulated Class E voltage and current waveforms and break them down into their harmonic components. So for example, here's the composite current waveform, which is the sum of the fundamental, the second harmonic, the third harmonic, and so on. And what's really interesting for the Class E case is that these harmonics provide a significant boost to both the voltage and current signals, which causes the reliability challenges, yes, but it's also what provides the great efficiency. From a microwave circuit designer's perspective, Class E network design is just a matter of providing the right impedances to the right harmonic frequencies to get these Fourier components. So any frequency domain circuit topology that does this will deliver the time domain waveforms that we want. And the best part is there are lots of circuit topologies that can potentially do this, and usually you only need to match the first few harmonics to get very close to the ideal waveforms. But that being said, in the PA simulations, you should still include a lot of harmonics just to be sure that you're operating reliably. So now I'll attempt to synthesize a realistic Class E network for this gallium nitride PA. I took an educated guess at the circuit topology, and then I used circuit optimization to try to match the impedances. So here's my network. It's very important to include device parasitics to achieve the right waveforms inside of the device. That's what really matters for efficiency. So in this example, the Class E capacitor comes partially from the device parasitic capacitance and partially from an on-chip capacitor that I added. And then I go off-chip using wire bonds, and I did the rest of the match using transmission lines. And I set this simulation up to automatically import the target impedances from the verification bench that I used before and use these as optimization goals. So the optimizer adjusts the circuit values to try to give me those impedances for the first 3 harmonics. And here's my initial simulation before optimization. The targets are marked with X's, and of course the impedances are off. And here are the impedances after optimization. So you can see they're pretty close to the targets, but they're not perfect. So that covers the output, and after that I conjugate matched the input to 50 ohms and adjusted the gate bias to lower the conduction angle. And I ran the simulation, and here are the results for the full gallium nitride PA. So I got almost 90% efficiency at the output with good power and gain, and the waveforms, output power, DC current do match the predicted results from the synthesis tool very well. The only difference seems to be some harmonic ripple in the current, and also the voltage peak is slightly higher than predicted. And both of these are related to the realistic circuit imperfectly modeling the ideal network. To give you another data point, I went to Cree's website, registered for access, and downloaded a model for the CGH 60030D. This is a gallium nitride hemped mimic. And I followed the same design procedure to design a Class E power amplifier with this device, with bond wires and transmission line matching included. And I picked Cree because they give designers information about the parasitics, and they also provide access to the internal current source. These are must-haves for Class E PA design. And similar to my previous example, the initial results were excellent. So I got 90% efficiency with 15 dB of gain and 24.8 watts of output power at 1 gigahertz with a 28 volt supply. And here is the Cree PA simulation versus the initial waveform and power predictions from my Class E synthesis tool. And the best part is it only took me about a half hour to get to this point, so that's a pretty good running start. And there you have it, a Class E power amplifier from concept to circuit design. I want to emphasize that this is a starting point for Class E PA design. There's still a lot more to consider. For example, you might need to think about coupling, stability, and design sensitivity, or maybe you'll want to investigate how to make the bandwidth wider, in which case I think doing a refined load pull is a very sensible approach. Keysight has some great YouTube videos on all of these topics too. And dealing with these types of challenges is all the more reason to get a head start by downloading this workspace. It includes the example that I showed today, and you can even drop in your own device. Good luck, and thanks for watching.